everybody to our first webinar about discovery of co-crystals. I see that many people are attending the meeting. I hope everybody can hear me well. Before we start the webinar, I'd like to give you some general information. If you have a question during the meeting, you can always send us an email to crystal16support@avantium.com, or you can also use the chat function inside the software. At the end of the presentation, Joop will answer your questions, and we will also place all our questions on our LinkedIn page so people can see what has been discussed. After the meeting, we will also send the slides to everybody subscribing to this meeting. I hope you will all enjoy the lecture, and I will give over the microphone to Joop de Horst.
Good afternoon. Welcome to the webinar on discovering new co-crystals. You can see my pointer on the screen, I hope. So this is the lecture, discovering new co-crystals by using solubility measurements. I am Joop de Horst, and I'm from Delft University of Technology. You can see my email, so if you have questions, you can contact me or also Avantium directly. So confidential questions I can answer as well. I also added my LinkedIn page, so you can connect by LinkedIn. I am assistant professor at TU Delft. And I'm actually investigating application-oriented fundamental aspects of crystallization processes. And I think co-crystals are one of them. So this is a small overview, say a small resume from the article recently published on crystal nucleation together with Roger Davy and Sven Schröder. It's also a very nice article about crystal nucleation. So I'm experienced in crystallization. I investigate crystal nucleation, co-crystals, but also pharmaceuticals and innovative crystallization processes. Like you see here on some recent publications. You can find all my publications on Scholar Google, and the link is on the upper right of this slide. And I am always very interested in working together with industry, tackling industrial problems, usually quite fundamental in nature as well. And that is where my interest lies. So if you have problems which you want to have investigated, I'm happy to help. So co-crystals. Co-crystals are defined as crystals that consist of two or more components that are in their pure form solid at room temperature. And the Dutch artist Escher has made some nice pictures representing these kinds of co-crystals in 2 dimensions. So on the left you see a fish crystal structure, only consisting of fish, and on the right you see a fish-bird co-crystal, so 1-to-1 co-crystal of fish and bird. So both components in this co-crystal determine the properties of the co-crystal, and they also determine the system thermodynamics as well as the crystallization kinetics. So you can see very different behavior going from a fish crystal to a fish bird co-crystal. And you can exploit that in real life by, for instance, looking at this molecule. This is a very large molecule for which they had difficulty crystallizing, but together with this aiding compound, this dicarboxylic acid you see in the middle, it could be co-crystallized. And you see a crystal of this co-crystal. You see a picture of this co-crystal on the right of the slide. So co-crystals can be used to avoid amorphous compounds and sulfates, for instance. But they can also be used to completely change crystal properties, to stabilize an API towards humidity, for instance. Or you can increase bioavailability through advanced dissolution rates. And also a funny, interesting thing is to combine multiple APIs in one co-crystal. So, for instance, aspirin and carbamazepine. It is said that carbamazepine has the side effect that it gives you a headache. So, if you co-crystallize it with aspirin, you avoid the side effect of carbamazepine. But of course, you could also add the crystals, the pure crystals themselves, in the pills. Another interesting thing for co-crystals is that you can use them in your process to improve your separation. So, for instance, make crystals that are more easily filtered off, so that your process is is much faster. So you can actually fine-tune properties of pharmaceutical solids by using co-crystals. So that brings us to the question how you design co-crystals. You have a vision that you want a certain product to have optimal product properties like dissolution behavior, and for that you need specific co-crystals, and you have to choose your co-former. So design your co-former to get to the right product properties. So that's quite a difficult question. And the first question, partial question to answer, is that given a combination of API and co-former, how to discover a co-crystal? How are you sure that that this API and co-former can form a co-crystal? So we're looking for a fast screening method for combination of API, co-former and solvent. And this is published in 2 articles of mine, of which the reference is shown here. And if you give me an email, I can send you those articles if you don't have them yet. So, discovering new co-crystals. And we are going to use the equipment of Avantium for that. So we are working in solutions, and then the solubility of these solids is a very important parameter. So the first thing I want to discuss is the solubility of solids. So here you see a typical eutectic phase diagram of compound A and B. So compound A has a lower melting point. So the melting temperature against composition is given in this diagram. So on the left axis, the A indicates the melting temperature of the solvent. So above that we have a liquid above the 2 lines. And on the right you have the solubility line of the solid B. So if we are at very high temperature, at a specific composition, for instance, the temperature and composition I indicate with the mouse arrow, And then if we cool down, we will cross the solubility line, and at some point we will start crystallizing, and then you form your crystals and you have crystals in a suspension. And well, you want to know the solubility of these crystals, so if you then slowly heat them up and record the temperature, and then there will be a temperature where the solution becomes a clear solution, and that is the saturation temperature if you measure accurately enough. And this saturation temperature is you know the composition of that saturation temperature, so you know a solubility point in your solubility graph. So here you see that usually solubility increases with temperature. So we measure saturation temperatures. So you start with a suspension, and light is going through this suspension. So it is actually blocked because the crystals are present. And at some point you will get a clear solution, and light is going through the sample, so that you can really measure that you have a clear solution. And that clear solution will be at high temperature, and the suspension will exist at low temperature. And then we are interested in the point where these crystals disappear, so the clear point, the temperature at which a suspension becomes a clear solution during heating with a certain rate. And that is shown in this graph. So the temperature against measurement time. The orange line is indicating the temperature profile we are using. So you cool down, and at some point you get a suspension, and then you heat up, and at some point you get a clear solution, and then you get 100% transmission. That's on the right axis. That's the green line. And at the point where you have 100% transmission at the temperature, that is your clear point. So the clear points are indicated by the red marks. And you can determine the saturation temperature from that. And if you do that multiple times, you see that the saturation temperature hardly changes. So that enables you to get solubility data within 1 day. And well, you have to use a specific heating rate. So we investigated how the heating rate influences the saturation temperature. So one specific composition, and we measured the saturation temperature multiple times with a specific heating rate. And you see that the lower the heating rate, the lower the saturation temperature. So there you see that the crystals get enough time to dissolve when you increase the temperature. So upon decreasing the heating rate, you get closer and closer to the thermodynamic solubility point, and that is actually what you want to know, the thermodynamic solubility point. So with a heating rate of around 0.3 degrees Celsius per minute, we have a relatively fast measurement, and our saturation temperature is close to the thermodynamic solubility point. So usually we use around a heating rate of around 0.3 degrees Celsius per minute. And then you can measure the saturation temperature of specific compositions, and usually that is plotted as this composition versus temperature. And then, for instance, for Isonicotinamide in ethanol, you get this diagram. And you see that solubility increases with temperature. You can describe these points. with, for instance, the van 't Hoff equation, which is giving the solubility of an ideal system. So you have the solubility, which is marked as X star, so mole fraction, here millimoles per mole. And that's described as a function of enthalpy of fusion of the pure component, so in this case isonicotinamide, and the melting temperature of the pure component. And this is a theoretical description, but we can use a fitting equation by with which you have two parameters to fit the line to, and we can do that in a van 't Hoff plot. So then you plot the log of x versus 1 over the temperature in Kelvin this time, and if all is well, you get a straight line, and that can be fitted with this equation, and you can determine A and B, and then you can extrapolate and interpolate the solubility data. So then you can determine the composition you need to get a saturation temperature of, for instance, 40 degrees. And this van 't Hoff equation is often more convenient and accurate to extrapolate. So usually we use this some sort of the van 't Hoff equation to fit our data. So we can determine saturation temperatures of samples with specific compositions and describe it mathematically. So that means that we can determine the phase diagram in a binary system of pharmaceutical and solvent. And we can also extrapolate to obtain the solubility at a certain temperature. So that is important because we are going to use that to discover co-crystals. And we do that in ternary systems, so at least 3 components. So we are looking for a fast screening method in a solution to discover co-crystals and alongside get valuable thermodynamic data which we can use in the design of crystallization processes and in obtaining single crystals, for instance. And we want to use small amounts of components and a relatively small number of experiments, while we want to have a high success rate. And this high success rate means that we want to screen at the right composition. So we need a certain concentration of, for instance, in this example, carbamazepine, and a certain concentration of isonicotinamide. But what concentration do we need to have the highest success rate for making co-crystals? So let's first determine the solubility of isonicotinamide and carbamazepine in ethanol. So here again is the mole fraction against the temperature in degrees Celsius. And the blue line is isonicotinamide, and the red line is the solubility line of carbamazepine. You directly see that the solubilities are quite different. So the isonicotinamide solubility is at least 6 times higher than the carbamazepine solubility. And we can determine now the solubility at 25 degrees Celsius. And for isonicotinamide, that is 33.3 millimoles per mole. And for carbamazepine, it's 5.7 millimoles per mole. So it's 6 times higher solubility for isonicotinamide. And we will have to account for that in our discovery of the new co-crystals for isonicotinamide and carbamazepine. So we can make now a ternary phase diagram. So carbamazepine, isonicotinamide, and the solvent is ethanol. And we can do that at 25 degrees because we now know the solubility of the pure components. And that is given by the spheres, the circles. The blue circle is the solubility of isonicotinamide in ethanol at 25 degrees, and the red circle is the solubility of carbamazepine in ethanol at 25 degrees. So now we can assume that we have an ideal system, and that means that isonicotinamide and carbamazepine do not influence each other's solubility. So that means that we can draw solubility lines in this diagram. One for a horizontal line for isonicotinamide solubility, so it will be constant even though we add carbamazepine to the solution. And the same is for carbamazepine, so that will be a vertical line, and they cross each other somewhere. So within this square given by the blue line, the red line, and the axis, you will have a solution if your co-crystal is not much more stable. So where do we want to screen now for co-crystals? So you will need both isonicotinamide and carbamazepine to be present. Well, we can say that the product of the mole fractions of carbamazepine and isonicotinamide should be as high as possible to give the highest chance for co-crystals. And then we come to the conclusion that the best condition to screen is this green point, which is determined by the pure component solubilities. So this green point is a very important point for screening for co-crystals, while it is determined by the pure component solubilities. So that is something you can measure and establish before you are going to look for co-crystals. So a more stable co-crystal will have a lower solubility, and that means that it will have a higher saturation temperature. So this diagram is valid for 25 degrees. So if we measure the saturation temperature for the green point, for a sample that consists of the green point, and we measure a saturation temperature that is higher than 25 degrees, we can assume that this is due to co-crystal formation. So we make a composition, a sample of the green point, and then measure the saturation temperature. And if this saturation temperature is higher than 25 degrees, we have a strong indication that co-crystals exist of isonicotinamide and carbamazepine. So that's what we did. We took the solubilities of pure carbamazepine and pure isonicotinamide at 25 degrees, and that is 5.7 millimoles per mole for carbamazepine and 33.3 millimole per mole for isonicotinamide. That is actually a ratio of 1 to 6 in the solution, so you need an excess of isonicotinamide. And then we measured the saturation temperature. And the saturation temperature of this composition is 42 degrees. So that is 17 degrees more than our reference temperature T. So saturation temperature is higher than our reference temperature, 25 degrees. So we have made a carbamazepine isonicotinamide co-crystal. And we can also do that at different reference temperatures. So here you have the reference temperature. So the lowest line is the line we talked about in the previous slide. But we also measured at different reference temperatures. We measured the saturation temperature. That's the green numbers. And they are all higher than the reference temperature. So we can actually nicely plot the difference between saturation temperature and temperature against the reference temperature. And then you get the graph that is on this slide, and you get the 4 points that are somewhere around 22 degrees on the y-axis, so saturation temperature minus reference temperature. And the nice thing of this graph is that you can also plot other systems in this graph. So you can actually summarize your whole screening procedure within one graph. So here is the saturation temperature minus the reference temperature for a number of systems. And well, we just arbitrarily chose 10 degrees as a point where we think if we have a temperature difference larger than 10 degrees, we have good indications that co-crystals exist. And that is true not only for carbamazepine with isonicotinamide, but also with nicotinamide, that's the red points, with nitrobenzamide, that's the squares, and benzamide, that's the black squares. But we see that the reference temperature is around 0 or even lower for two co-formers, that is picolinamide and ethoxybenzamide. So that those temperatures indicate that you don't form a co-crystal, and probably they deviate at high temperatures because there we don't fit the solubility of the pure components accurately enough. So we can do that also in different solvents. So instead of ethanol, here we see results for butanol. So again, large temperature differences for carbamazepine with isonicotinamide and nicotinamide and benzamide, but picolinamide does not seem to give co-crystals. Also for cinnamic acid we found some co-crystals. A large temperature difference for cinnamic acid with isonicotinamide, and also for cinnamic acid with nitrobenzamide, and then no co-crystals for picolinamide with cinnamic acid and ethoxybenzamide and cinnamic acid. So then we come to this screening method. So I talked about the first two steps, so determining the pure component solubilities, and those solubilities determine where you have to screen for a co-crystal. So we choose a certain temperature, determine the pure component solubilities, make a sample with composition of these pure component solubilities, and then we measure the saturation temperature. And if that saturation temperature is higher than our reference temperature, then that is a good indication that we have co-crystals. But you can also do the co-crystal discovery just by crystallizing them and making a XRPD pattern, of course. As long as you know the pure component solubilities, you know where to screen for co-crystals, and you can screen for co-crystals as long as you have a good preparation method for your co-crystals. So usually that can be cooling crystallization, but it can also be evaporative crystallization. So notice that we don't use a stoichiometric solution, so 1-to-1, because our compositions to screen are governed by the pure component solubilities, which can be quite different for the different components. So if we have indications that co-crystals exist, we can analyze them with XRPD, and we have other methods of preparation. And the nice thing of this method is that you get additional information to make a phase diagram And this phase diagram you can use for single crystal preparation and also for crystallization design later on in the development. So that is what I want to tell a little bit more about. So now we want to derive a phase diagram for the co-crystal system carbamazepine and isonicotinamide. So then we assume that the solubility of the co-crystal is determined by the solubility product. And we have measured our saturation temperature of the co-crystal of carbamazepine with isonicotinamide, and we know the concentrations we used. So we can determine the solubility product of the co-crystal, so the mole fraction of carbamazepine times the mole fraction of isonicotinamide, and we know the saturation temperature that belongs to that solubility product. That is the green number that is in this row. So we can plot that. So the solubility product as a function of temperature, and we get this red line. And also here you can use the van 't Hoff equation to plot this. But here I use just the solubility product against temperature, and I indicate here a temperature of 25 degrees, and then you can establish that your solubility product of the co-crystal is 53. So that you can use to construct a phase diagram at 25 degrees. And that is shown in this slide, where here is on the x-axis is the concentration of carbamazepine, so the mole fraction, and on the y-axis the mole fraction of isonicotinamide. And we know the pure component solubilities, so the red line for carbamazepine, the blue line for isonicotinamide, and then in between them, connecting them, is the solubility line for the co-crystal. And this line is governed by the solubility product of 53. And you see that the stoichiometric line does not really go through the co-crystal region. So if you would crystallize isonicotinamide and carbamazepine from 1 to 1 stoichiometric solutions, you would not obtain co-crystals from those solutions. You need solutions that contain about 6 times more isonicotinamide than carbamazepine. So we can now use our van 't Hoff fits to investigate whether our phase diagram is right. So this is saturation temperature of samples, and these samples contain isonicotinamide and carbamazepine, but isonicotinamide concentration decreases going to the right. So on the left you have pure isonicotinamide in ethanol, and on the right you have no isonicotinamide in ethanol. And for carbamazepine it's the other way around. So on the right we have pure carbamazepine in ethanol, and on the left there's no carbamazepine in the solution. And so isonicotinamide gradually decreases going to the right, and carbamazepine concentration gradually increases going to the right. And that's a convenient way of screening the phase diagram with saturation temperature measurements. And the lines I indicate here are from our pure component solubility measurements. So that's the lines going down from the right and from the left. And in the middle you see this bump. That is our estimate from our our saturation temperature screening that took place exactly at this point where both solubilities cross. So, well, exactly. So the saturation temperatures are that we measure for these different compositions are relatively close to the solid line. So the phase diagram estimate we make is a nice one, a first nice one. And if we do these measurements, we can even increase the accuracy of this phase diagram. The small deviation you see here is due to non-ideality. There is some influence of isonicotinamide on the solubility of carbamazepine and vice versa. And you see that in this by measuring it in this way. That things do not always work, you see in this diagram, where we determined in a similar way as in the previous slide the phase diagram for Ethanol with Cinnamic acid. And you see that Ethanol has a very high pKa and Cinnamic acid has a low pKa, so they must form a salt if they crystallize together into one crystal. And you see that if you have dissociating molecules here, then you might end up with a large deviation. If you look at the pure component solubilities, you would want to screen here at the point where these two solid lines cross. But if we determine this diagram, you see that you have the largest possibility around the 1-to-1 stoichiometric solutions. But that is for compounds that dissociate due to the presence of another compound. Okay. So one thing you can do if you know the phase diagram is to prepare a composition here in this point. So you add pure crystals of carbamazepine to a microscopic vial in such a way that you get this concentration in the end if you also add the solvent. You can also add Isonicotinamide crystals, and then you get this composition. And the moment you add ethanol, the crystals will start to dissolve and concentration increases, and you will enter the co-crystal region, and you get supersaturation towards the co-crystal, while you get undersaturated solution towards the pure components. And you see that in this movie. At least I hope that that works in this webinar. So you see in the middle here, there are needle crystals which grow out. I don't think the movie is working. So what I saw in this movie was that these needles grow out. So these are the co-crystals, and the other crystals disappear. But at some point also these needle crystals start to dissolve, and other crystals pop up somewhere else in this view. So actually what we discovered is that we have two polymorphic forms, so form 1 and form 2. And in the movie, which you did not see, we see first the form 2 appear, that is the needle form, which then later on transform into form 1, which is the final stable form at room temperature. So this is actually a very easy and interesting way to make the co-crystals just by adding the crystals to a vial, add the solvent to the vial as well, and then just stir. And as long as you are in this green point and there is a co-crystal, you know that eventually co-crystals will start crystallizing. Okay, I think I reached the end of my presentation. Actually, you can achieve even more with with the thermodynamic data you get from saturation temperature measurements, and well, you can ask me about it, and you can also read my articles in which I explain, for instance, that you can use saturation temperature measurements to determine whether you have a conglomerate system or a racemic compound system for chiral molecules. So that was the webinar. You're free to ask all kinds of questions, and I try to answer them either by email or at this moment. So thank you for your attention, and if you have questions you can ask them here, and you can also drop a line to Dennis Tam or me, and we can post the answer on the LinkedIn page, or we can directly send you an email back. So thank you for your attention.
So here is Danny again. I see at the moment there are no questions. If you have questions later, or you want a copy of the article, feel free to contact Joop or me. We can send it to you. And we also recorded this webinar, so we will place it on our website. If there are no questions, then I think I will stop the meeting. And hopefully we will meet you again with our next webinar, which Joop will also present. And we are now discussing the topic. Okay, I will stop the meeting now, and wish you all a very nice day. Bye.